So in this video, we're going to talk about how you can compute the equivalent resistance of resistors that are connected either in series or in parallel. So remember that a series connection means that two components share only one common point of connection. In parallel means that they share two. So what I have depicted on the left here are 1, 2, 3, 4 resistors that are connected in series. Note that if any current were to be in R1, it has no choice but to go through R2 and also go through R3 and also go through R4. So as we'd expect, when these resistors are in series, they have the same current in them. On the right, though, notice that R1, R2, R3, and R4 are connected in parallel. They actually share two common points of connection. So current actually entering this node in the circuit must make a choice and branch either through R1, R2, R3, or R4. So what we're going to find is that the majority of current will go on the path of least resistance. So in both of these two configurations, though, we can talk about an equivalent resistance, which just means how much total resistance is this configuration of resistors providing. So if they're in series, what's going to happen is, if you think about it, if you were current and you have to go from this node to this node in the circuit, you got to push through R1, then you got to push through R2, then you got to push through R3, then you got to push through R4. So the equivalent resistance is actually going to be the sum of each of those individual resistors, R1 plus R2 plus R3 plus R4. Versus when they're in parallel, if you think about it, it's not really the resistance that's summing, it's that idea of conductance that we talked about in the prior slide. Namely, if I'm current and I get to choose whether I can branch through R1, branch through R2, branch through R3, or branch through R4, each of those kind of resistive paths is providing an additional path of conductance for me. So the total conductance is actually adding up. And if you actually equate those to formulas, this is what it looks like. The formula for the resistance of the equivalent resistance of resistors in series is actually really simple. You're just going to add up all of the individual resistance values. However, if you look at the formula in parallel, it looks a little bit tricky. And the reason that it's tricky has to do with the fact that when resistors are in parallel, it's not the resistance that's summing, it's actually the conductance. So remember that the inverse of the resistance is nothing more than the conductance. So really what you're adding inside the parentheses is all the individual conductances. And then you're taking the inverse of that to go back to units of resistance. So even though this formula looks really tricky, physically it's pretty easy to understand, but that doesn't mean it's easy to use. What we're going to need to do is take the inverse of each resistance, add them together, and then take the inverse again. So let's look at a little bit of an example problem here. And you notice I was turning on my webcam. But the first question, we're given three resistors, a 1 kilo ohm resistor, a 2 kilo ohm resistor, and a 1 kilo ohm resistor. So I'm not even going to write in, no, I'll write them in. 1 kilo ohm, 2 kilo ohms, and 1 kilo ohm. And this is A, and this is B. And the question is, what is RAB? So what that means is the equivalent resistance from node A to node B. So if you're current and you have to pass from A to B, notice that these three resistors are connected in series. You can either say that they share one common point of connection. One node of R1 is connected to one node of R2. One node of R2 is connected to one node of R3, and so on. Or you can say if there was current in the circuit, the current in R1, R2, and R3 would be the same because there's nowhere to branch. So what that means is that RAB is going to be R1 plus R2 plus R3 because these three things are in series. And then what I need to do then is just to add these up. So remember that kilo is just a scaling. It means 1,000. Ohms is the actual unit. So sometimes people actually look at a kilo ohm as actually being a unit of resistance. It's just the base unit of resistance, ohm, scaled up by a factor of 1,000. So that's exactly what I'm going to do. I'm going to say that I'm adding these three resistances. They technically all have the same units of kilo ohms. So I'll just add the actual quantity, and my result will be my answer in kilo ohms. So 1 plus 2 plus 3 is just 6. So that shows us that that resistance value is 6 kilo ohms. So for the next question, we're given a parallel configuration. If you notice, we have R4, which is a 3 ohm resistor, R5, which is also a 3 ohm resistor, and R6, which is also a 3 ohm resistor. And what we're asked is to find the equivalent resistance from C to D in this circuit. So the idea of how this actually operates is if current were to go in C and then go to D, it has three branch choices that it can make. R4, R5, and R6 are connected in parallel. So the equivalent resistance for this actual case, let me put that up real quick, is just going to be 1 over R4 plus 1 over R5 plus 1 over R6, and then take the inverse of the entire thing. And remember that each of these, 1 over R4, is just the conductance of this path. 1 over R5 is just the conductance of this path. Same thing for R6, so you're just adding those together. But we want to express our answer in terms of resistors. So what is this going to be? Well, it's just going to be 1/3 plus 1/3 plus 1/3 inverse. These all have a common denominator, so I can just add the numerators. And what that's just going to be is 3 over 3 inverse, or just 1 over 1 inverse, which is just going to be 1, in whatever the unit that I was kind of omitting the entire time, which is ohms. So you see an interesting thing there. When resistors are connected in parallel, the equivalent resistance of the configuration actually is less than any of the individual resistors in the configuration. And that's true. And what that means is if I were to change one of these from 3 to 2, the equivalent resistance would even go down further, and it would always be less than 2. There's also a special formula that you see here, where if you connect the same resistor in parallel n times, what it effectively does is it divides the equivalent resistance by a factor of n. So hopefully that all made sense to you. We're going to get a chance to do some more examples on the homework this week.